The Secret of Flight, a series of programs on aerodynamics. Program 13, Modern Problems in Flight. Your host is Dr. Alexander Lippisch.
When in October 1947, Major Jaeger, with the experimental rocket plane, the Bell X-1, took for the first time the speed barrier, a new era of flight was born. The flight in the range beyond the speed of sound. This is a picture of this aircraft, which is the first supersonic aircraft ever built. Now, you might ask the question, what has the speed of sound to do with flight? And why have the scientists all the time talked about the speed barrier of the speed of sound? Well, as you know, the speed of sound is roughly 770 miles per hour. And if I here make a small disturbance, a noise, I make lots of noise, but I clap the hands here like this, then this sound travels away with a speed of 1100 feet per second. And if somebody, for instance, stands away 13 miles, he would hear that clapping just 1 minute after it happened. Now, what is sound? Sound is the pressure, the pressure waves which are created by such disturbance. And the speed of sound is the propagation speed of such pressure waves which go through the air. That means, well, since it is the speed of pressure propagation, and since our aircraft are supported by pressure fields, this speed is also the propagation speed of the pressure field around an aircraft. Now, let's imagine this. Let's imagine there is an aircraft flying a straight course just horizontally ahead. And as you know, it's supported by pressure underneath the wings, suction above the wings, and all this other thing around fuselages and so on. Now, if you imagine just a little tiny particle of air which is ahead of this aircraft. While this aircraft comes along, its pressure field is propagated, and this little particle gets a tiny signal that there is coming Captain Smith with a big airliner, and the little particle, well, polite as air now is, begins a motion to get fine and smooth over Captain Smith's airliner. Well, that's all right, as long as this airliner flies below the speed of sound, below the speed of the propagation of its pressure field. But if now Captain Smith comes with a slick supersonic airliner, well, then this little particle doesn't get any signal before the airliner is there. And suddenly there is Captain Smith and the airliner and the little particle. What happens? A collision happens. And well, it's not very serious because air is not a solid matter, and it is compressible. a compressible gas. And due to this coming together, the air is compressed through a shock wave, and all the particles which are now hit by the wave of the airplane will get a sudden compression shock and a sudden deflection. Therefore, in the subsonic range, the flow field is uniform all over. And in the supersonic range, we have a complete difference. Now, let's go to these charts, which might explain the thing a little bit more clear. You see, here is Captain Smith in the subsonic range, and the pressure waves which are created by small disturbances go out all over because they run out the speed of the airplane. They are far ahead of him, and the farther he flies, the farther ahead are these pressure waves. But if we think now of a supersonic speed of the airplane, then these waves which go out in circles would not reach any space which is on the sides or ahead of the airplane outside of this cone, which is formed by the pressure waves which are exerted from this airplane flying at supersonic speeds. And there is a very distinct cone formed in which only the air can be under the influence of the pressure field around this airplane. Now we call this cone angle, this cone, the Mach cone, and we call the ratio of the speed of sound with respect to the speed of the aircraft, we call it the Mach number. So that if somebody flies, for instance, with a Mach number of 2, that means that he flies 2 times the speed of sound. That would be roughly 1,500 miles per hour. Now there is another very interesting and significant difference between the subsonic and the supersonic flow. When you think, well, you want to make high speed through a nozzle, then you might have a big tank and pump it up, and then have a little nozzle and let the air out. And the more you pressurize the air in this vessel, the higher the speed will be. Yeah, up to a certain point. You will find out that you pump it up as much as you want, and you don't get out of this opening more than the speed of sound. Therefore, we have to devise a new type of a nozzle. The first man to design such a supersonic nozzle was Pierre de Laval, and therefore we call a nozzle which is now first convergent and then divergent a Laval nozzle. This is necessary because due to this increasing in speed and decreasing in pressure, the density of the air gets lower and lower, and therefore beyond the speed of sound, the density decreases more than the speed increases, and we have to open up. And in the supersonic range, acceleration means a widening of the streamlines, and deceleration to get the streamlines nearer together. In the subsonic range, it's just reversed, as we know, because when we want to make more speed, then the streamlines have to come together nearer by. And diffusion means deceleration. Therefore, all these geometries of the flow fields are completely changed. In the subsonic range, we see that the flow is completely symmetrical. And when we neglect the friction, the forces are in balance. But when we think about the same hump and a supersonic flow over it, then we see at once that we have in front a pressure on the surface and at the rear a suction on the surface, which makes, since this is the pressure force, this is the suction force, which makes a component of the forces in the direction of the flow, a drag component besides of friction drag. This is the wave drag of the supersonic flow, which then necessarily has a strong influence on the efficiency of the supersonic aircraft and diminishes the range and makes it necessary that such aircraft have large power and a large fuel consumption. On the other hand, as we see it here, also the pressure distribution on the wing changes considerably, and we have a shift in the center of pressure, which was here at the first quarter of the airfoil, and here is almost at the center. This makes a stability problem in the supersonic range. But let's look now at some pictures which we have from the flow in supersonic wind tunnels and in nozzles. They are made by the so-called Schlieren method, and what we see is the density changes in such flow. These pictures are made available by the National Advisory Committee for Aeronautics in Langley Field, Virginia. We see a thin airfoil in the transonic range. That means going from the subsonic flow into the supersonic flow range. At the present time, we see what is called buffeting. That means we have a formation of oscillating shock waves on the both surfaces. Finally, these oscillating shock waves come together into one straight shock, which is now beginning to form at the rear part of the wing, and with increasing Mach number. You see it from the finger, which moves down on the scale and which is now in the range of something above 0.9 Mach number. The shock travels backwards towards the trailing edge and finally forms an oblique shock, so that the whole flow on the surface of the wing is supersonic, which you also see from the slim Mach waves which are generated from the surface of the wing. Now we reach the Mach number 1 and the flow is completely supersonic. Another interesting effect can be seen in the jet stream from a rocket or a jet engine in the supersonic range. You see waves forming in such supersonic stream, which is here on the first supersonic aircraft, the Bell X-1. And we see it now here as an experiment in our laboratory, where we have a nozzle on the left-hand side. The jet stream comes out with supersonic speed, and the dots we see are the waves which are formed in this jet stream. The more we go down to the sonic speed, the smaller the wavelength gets, and finally our stream disappears completely when we have subsonic flow in this nozzle. Now, when you think of all these problems which arise from the flight in these high speed ranges, then you might realize that the original concept of the aircraft as a powered glider is probably not the final solution of the aircraft for the use of human communications. See, in the meantime, while we were working on these high-speed problems, a new type of an aircraft came up. This was a helicopter, which could fly without any speed. And it has taught us a very important lesson, that such a feature, to hover and to raise from just a tiny spot on the ground and to come down on it, is so important that, well, many other things are not important with respect to difficulty of obtaining such features. So the question is, can we combine this low-speed aircraft with our high-speed aircraft in one new conception? And when you think about it, you come to the conclusion that this certainly might be possible, but that we have to have then an aircraft which is not derived from the natural prototype, but which we conceive from scientific and technical information. A man-made flying machine. Now we have begun with this work, and to distinguish it from the aircraft, the powered glider, which is called the aeroplane because it has planes, we call such types an aerodyne, a body which is dynamically lifted. And this dynamic lift is made by an internal flow system. Now, we are just at the beginning of such development. And I can show you here one of the first models which we have developed from this type of an aircraft, so that we might show to people what we mean with this development. You see, this is a small model which is lifted by a row of 4 shrouded propellers. You remember, as I have shown them to you in our propulsion program. So in each of these holes, as you might call them, is an electric motor which drives a little propeller. The stream which comes out and lifts the thing goes over certain control surfaces which are down there. And these are stabilized by a gyro system, and I can also control them from a seat. The electric power comes in through this cable, since we cannot carry batteries in such a thing. And also the control signals which I give from the seat go also through the cable. You see, we have an undercarriage, and when I have good luck, then I can take it off and bring it down. Now this is the seat, and you see I have a normal control like in the pilot seat, and from here I can switch in the power for the gyros, as I do it right now. And then when I switch in the power for the engines, the thing will take off. Now we will try another flight with this model. You know, this model was designed about 4 years ago, and it actually serves the purpose to show that you can stabilize a flying body in the low-speed range. And this was the purpose of this model, and we obtained this purpose by using certain gyroscopic action to control flaps to stabilize the thing in flight. Now, let's try it. Now, the models I have shown to you in flight are just the beginning of something which has to be developed into an efficient aircraft type. To give you a little imagination of what might come of such a development, we have here in the tunnel a model which might illustrate the use of such internal flow systems which give lift and forward thrust and can be used in the flight at no speed as well as in the supersonic speed range. We come now to the end of our program, and I want to thank all of you who have watched The Secret of Flight go on the air. I want to thank also the Office of Naval Research and the Collins Radio Company, who have given the permission that we could use this smoke tunnel and some other equipment. We have tried to give you a short glimpse into the wild field of aeronautics. And we hope that we have raised your interest on several problems in the field of aviation. Our time was certainly short, and we couldn't show you many things we would like to. But nevertheless, the few examples we could demonstrate were, as I hope, of a more general interest and gave you the idea of what might come out of this development in the future. See, the work of the scientist and of the engineer in this field is certainly not an easy task. And it is necessary for the evolution of new principles and of new knowledge that this is carried on from one generation to the next. Despite of the tremendous progress which has been made in these first 50 years of aviation, many problems still await their solution, and every day opens up new fields, new views, new aspects in this new science. As you know, today, aviation serves mainly and to a large part as a defense of our freedoms and as a deterrent of war. But besides of it, aviation has flung his arms around the world to bring men to men and to create mutual understanding and new friendships. You see, to break the speed barrier was a scientific and technical problem, but this may serve at last to solve a great human problem, to break the barrier of fear and distrust, and to bring love and happiness to all men. Thank you and goodbye.
You have just seen Modern Problems of Flight, the 13th in a series of programs explaining the secret of flight. Your host has been Dr. Alexander Lippisch, Director of the Aeronautical Research Laboratories of the Collins Radio Company. This program was produced for the Educational Television and Radio Center by the State University of Iowa.